Recording in progress.
Okay, I guess that's our cue. We should get started. So this is the second quantum engineering session. Okay, unfortunately, we're across from Olga's sessions, so we're drawing some of the same people. But we seem to be having a reasonable attendance. Okay, so our first talk will be given by Vlad Shalayev, and it will be on quantum metaphotonics.
So Phil, I assume you could see my screen and hear me, right?
Yes.
Yes, all looking good.
Okay, no excuses not to talk. Well, let me start with thank you guys, Alexei and Phil, for putting together this very timely seminar and for inviting me. So what I'm gonna cover in this presentation is basically single photon based quantum photonic circuitry in silicon nitride, which is resulted from our recent discovery of the single photon emitters in this very important material platform. And then I also spent some time showing that plasmonics, old beloved plasmonics, actually could make a difference for quantum photonics through speeding up processes, quantum processes, and making them immune to decoherence. When it comes down to quantum, there are lots of different material platforms which different groups pursue. Clearly, there is a trade-off between interaction strengths, where superconducting qubits are probably the best approach, and coherence time, where I believe photons are unbeatable because they are very immune to decoherence, with many other different materials in between based on various color centers, trapped ions, trapped atoms, and other material platform. But one thing is clear, that no matter which material platform would be used, photons will indeed play a very essential role there. Because after all, photons are unparalleled units of information. They propagate with the highest possible speed, which is speed of light, and they're very immune to decoherence, as I pointed out. And therefore, not surprisingly, arguably the most spectacular demonstrations so far of quantum supremacies were all based on photonics. You could see here, one is about this quantum communication via satellite shown by the Chinese group, and another one related to actually bosonic sampling. Most recent one demonstrated by Xanadu, where they did this sampling within a few microseconds. It's the task which would take 9,000 years for the best classical computer. So photons clearly would play a very important role. But the thing about photons here, they're very robust, immune to decoherence, but it's important to control them, to manipulate them. So basically, normally the coupling of photons to matter is very weak, simply because the wavelength is much larger than the size of a qubit or atom. But you do need to control it, and so ideally you would like to switch on and off strong coupling between light and matter. And that's actually where, for example, plasmonics could play a very essential role. So let me start with this silicon nitride-based integrated quantum photonics. This is our relatively recent effort, which started with discovery of single photon emitters. People were not able actually to have the single photon emitters before, for the reason that basically there is a very strong background in silicon nitride, which makes it impossible to see any single photon sources. And to our surprise, I should confess, it happened to some extent accidentally. So if you make silicon nitride in somewhat different way, specifically in our case, we use high-density plasma CVD, but most importantly, what we use, we enrich it with nitrogen. So it's not 50-50 silicon and nitride, but it's a nitrogen-rich silicon nitride. And when you do that, this fluorescence background truly dramatically decreases, like orders of magnitude, as you could see in this plot. And that's truly remarkable. There is some price we pay for this. It's the refractive index becomes somewhat smaller. but we are looking for other ways to make this nitrogen-rich silicon nitride. And there is indication that if, for example, if you will be using plasma-enhanced CVD, then refractive index would not necessarily be somewhat dropped, and we still would have this dramatic decrease in fluorescence background. So it's one thing, you need to get rid of this fluorescence background, but you also need to create these single photon emitters. And for that, the trick we played, again, it came a little bit unexpectedly, it's a very rapid thermal annealing. So first of all, you need to place your silicon nitride on silica substrate. It's important that because we believe these emitters, these defects which are responsible for single photon emission are created at the interface between silicon nitride and silica. And we think that the reason for that is simple, because the thermal expansion coefficient for silica, silicon dioxide and silicon nitride is different. And when you do this rapid thermal annealing, so you create strain, and this strain actually causes these defects which capable of single photon emitters. But one way or another, after you make this nitrogen-enriched silicon nitride and then do this rapid thermal annealing, you see this really very bright single photon emitters, which even at room temperature, which is indeed a very important thing for various applications. Here you could see some characteristics of our single photon emitters. This is room temperature measurements. You could see that G2 is actually quite impressive for room temperature. Basically, most of our emitters is below 0.2, and this is without any background correction or filtering, all these tricks which people use to make G2 as small as possible. And the smaller G2, the higher purity of your single photon emission. So the count is very high. So we basically get above 1 million counts per second. Again, it's room temperature. So linear polarization is expected for the single photon emitters. And the emission could be associated with 4 lines, E1, 2, 3, and 4, as you could see, and they're overlapping, giving this relatively broad emission line at to room temperature. So to understand better what's going on, what is the nature of these emitters, we did low temperature measurements at liquid helium temperature. And you could see here that in addition to the silicon Raman, a well-known line, we do obtain this really nice zero phonon line at around 548 nanometers. And you could see here, so different lines associated with these E1, E2, E3, and 4. But most importantly, when we look at the widths of this zero phonon line, we see relatively broad 0.26 nanometer line, but clearly it's inhomogeneously broadened because of the shape. And we believe this is all related to spectral diffusion. And to control this, we decided not to measure for a long time, like 150 seconds, where you could see clearly that actually there is indeed diffusion of this central position of zero phonon line. But if you do short measurements, like 5 seconds, then the line we obtained, it's much more narrow. It's going down to like 30 gigahertz only, which in our case basically comparable to the spectral resolution. So the next step, so we cannot actually say how narrow these lines at this point because what we measure is limited by the spectral resolution. So the next step would be to use photoluminescence excitation spectroscopy, which in principle allows us to get much more narrow lines. Or you could also do directly this Hong-O Mundell interferometry, which directly would measure whether your photons seem distinguishable or not. And for this quantum photonics application, that's the key thing, not to have just single photons only, but to have indistinguishable single photons. So this work in progress, and also there are some tricks how to control spectral diffusion, which are listed here with electrical field or strain tuning. So we now are working in all these directions. So we also asked some theorists doing these DFT simulations from Technical University of Denmark. And when they did simulations, what it looks like, if you at interface between silicon nitride and silica, replace one of the nitrogen atoms with oxygen and one of the silicon atoms with nitrogen, so you would get actually this type of defect. then the zero phonon line, which they predict, is around 536 nanometers, which is close to what we experimentally observe. So even though we cannot be 100% sure, but it looks like the defect we are dealing with is of this kind. And the other interesting thing, we repeatedly observe this three lines, V1, V2, V3, as shown here, which could be explained this by vibronic modes of this defect, which we are considering. So that's very important. As soon as we understand the nature of the single photon emitters, of course, we would be in a position to further develop and optimize it. So what else we did? We were able to couple single photon emitters to a waveguide, because eventually we would like to have this circuitry with potentially thousands or million emitters to do real like quantum simulations and other type of experiments. So it's very critical to couple them to waveguide. Here you could see that single photon emitters and silicon nitride waveguide. You could couple light to this waveguide through grating and out-couple it also through grating. And indeed, we obtained very nice G2, 0.15 in this case. So with signal coming from the single photon emitters in the waveguide, and then out-coupled by grating and sent to the detector. So the most important thing to accomplish, as far as we see it, is actually to create the single photon emitters deterministically. So in this effort, we actually made many pillars of silicon nitride sitting on silica substrate. And what we obtained that actually 67% of these pillars do produce these single photon emitters, which is actually surprisingly high, because it's clearly not random, not Poissonian controlled, and that was obtained without any optimization. So, and of course, the next step is just to place this pillar on a waveguide so that it could couple to a waveguide, and it also could be further optimized. We did this topology optimization, basically inverse design, and it shows that the best way would be to put this place in this kind of odd-shaped structure, and this, in this case, the coupling to the waveguide would be the highest possible. So this work again is in progress, but the important thing to point it out, which I already actually mentioned, that clearly we have non-stochastic source of single photons, because normally when you get these single photon sources by doing this ion implantation or thermal annealing, they are basically random. They are Poisson controlled, so you typically have like 30% success rate. In our case, without any further optimization, we obtained that all the pillars, we just arbitrarily picked up 55 pillars in a row, and all of them actually show G2 below 1, meaning that they show this anti-bunching, and 67% of them is below 0.5, indicating they are single photon emitters, which is way above of what you would expect in the case of random fabrication of single photon emitters. So hopefully, if you would be able to optimize it, we could bring this yield close to 100%, and that would open possibility to make this true single photon-based quantum photonic circuitry in silicon nitride, because all other elements needed for quantum simulators, they basically well known, and it's not difficult to fabricate them, like a bunch of Mach-Zehnder diffrometers. And of course, in the end, you should have these single photon detectors, which also in principle exist. So let me spend a few minutes in showing that plasmonics actually could be quite important in terms of making these quantum processes immune to decoherence. And the idea here is very simple. We know that if you have a plasmonic antenna, like shown here, for example, based on gap plasmon, when you have, let's say, a silver nanocube, a single crystal silver nanocube, and underneath epitaxial silver, and you put in between single photon emitters, for example, based on nitrogen vacancy in nanodiamond, then actually, because of this plasmonic speed up, the rate with which photon emitted could be much faster. And why it's important, it all comes to the point that how to control this light matter coupling. As I pointed out, because the wavelength is much larger than the size of atom, the coupling is typically very small, And the way to increase this coupling is to use this so-called Purcell enhancement. When you place your qubit in a cavity, and because photons are forcing back between mirrors, and coupled to your atom effectively many times, so the effective coupling increases. And the increase goes as a ratio of the quality factor of your cavity and inversely proportional to the volume of electromagnetic mode. And typically people use all type of dielectric cavities, such as the diffracting photonic crystals, where Q could be enormously high, up to, let's say, 100 millions, but V, of course, is diffraction limited in this case. But the problem to point out here, the higher the quality factor, the slower the process. You pay the price. And it means that you have to keep your quantum coherence, your quantum superposition for a really long time. So, and our idea is actually to go the other way around, to get this enhancement, but at very high speed. For that, plasmonics actually could make a difference. If you take, instead of really nice small plasmonic nanoantennas, such as a gap plasmon based, the volume of the electromagnetic mode is concentrated, could be as small as 5 nanometers. 5 nanometers is 100 times smaller than the wavelengths. So you raise it to the power of 3, you immediately get 10 to the 6 enhancement in terms of the coupling to light. And quality factor for plasmonics is not high, it's order of 100. So in total, you get the same Purcell enhancement, but Q is limited. It's only 100 instead of like 100 millions, like in the case of dielectric cavities. And this is actually good news rather than bad, because if Q is relatively small, then the response of your system is broadband and very fast. If Q is on the order of 100, means your system actually operates at terahertz rate. The central frequency is 10 to the 15. If Q is 100, you go from 10 to the 15, 10 to the 13. So basically, it's like 10 terahertz operational rate, which could outpace the decoherence rate. And that's the whole idea how plasmonics actually could make a difference for this quantum applications. So this slide further illustrates this idea. Typically, to protect this, to prevent this quantum decoherence, people use extremely low temperatures or trap atoms or ions. But what if we simply speed up the process? For example, if you're looking at the emission of single photons, if single photons would be emitted before decoherence happens, then it would be immune to decoherence. So the idea is just to make your process faster so that it would happen before quantum decoherence could play any role. And that's where plasmonics could play a very unique role, because I don't know any other system which could dramatically increase light matter coupling and keep the speed, really optical speeds, like at the range of 10 terahertz or so. So what we expect in this case from antenna is actually it should play twofold role. So the gap should be as small as possible, because the smaller the gap between the silver cube and the silver film, the smaller the volume of electromagnetic volume is concentrated. So the Purcell factor becomes higher. But another important thing, the antenna itself cannot be too small, because you need to outcouple these single photons before decoherence happens. It means that the rate of outcoupling should be high. It turns out that the size of this cube should be in the range of like 100 nanometers or so, and then the outcoupling rate could be not only the dephasing rate, but also actually the rate with which plasmons decay. So it would be like loss-free and decoherence-free system under optimal conditions. So this is our experiment, which was done some time ago already. Here we use nanodiamonds with nitrogen vacancies, which we place between the silver cube and silver film, as it's shown here. And we actually obtained quite dramatic lifetime shortening by 3,500, so that the lifetime was record short 23 picosecond. It's still not fast enough, because in nitrogen vacancy, decoherence rate is crazy. I mean, it's really way too fast because of strong coupling to phonons. So there are other single photon emitters where decoherence is not as large. And with the same type of plasmonic speed up, we should be able in that case to beat the decoherence rate. But at least it illustrates that indeed nanoantenna could provide this very, very strong speed up at the range of 10,000 and above. And that's actually what we need, because for good single photon emitters, decoherence rate is typically like picosecond. So and typical rate of single photon emission is nanosecond. So we needed to speed up roughly 10,000 times to beat the decoherence rate. And here, at least, we demonstrate that we close in terms of this rate to which we increase this emission of single photons. And that's actually a calculation showing done by Jacob Kurgin, that under optimal condition, when the size of the gap is like 3 nanometers, the size of antenna 60 nanometers, the efficiency of emission could be as high as 96%. And this is because it really outpaces any decoherence rate and any loss rate under optimal condition. And that's the whole idea which we are trying to pursue now in this effort for obtaining sources of indistinguishable photons. So in that regard, of course, other interesting candidates would be these HBN-based single photon emitters, and specifically this boron vacancy in HBN is known that it's able to provide this spin-dependent fluorescence, which means that it has this optically detected magnetic resonance contrast, ODMR contrast, and that's actually very good. It means that with light you could create spin and it could read out spin, which are very important for application. And of course, it could be used for all type of quantum sensing because it's basically 2D structure. So you could bring it to very close proximity of the material which you would like to sense. So we did first some optimization. Let's say if you use same type of antenna, epitaxial silver and silver cube, what thickness should have HBN and where the defect should be sitting. And we obtained that the depth of defect should be like 3 nanometers, and the thickness of flake should be like 6-8 nanometers. And to detect this ODMR, I mean, we made this silhouette in the form of this waveguide so that it could support this microwave excitations to measure ODMR. And we obtained pretty good spin contrast, 6%, which is quite good, measurable things. But importantly, if you compare the photoluminescence from HBN flake just sitting on this microwave waveguide and the one which is sitting between silver cube and microwave waveguide, so that you have this gap plasmon speed up. So we obtained that these 250 enhancement in the photoluminescence rate, as you could see here. It's truly dramatic enhancement. If you now take into account the size of the spot is actually larger than the size of the cube, so, and of course, outside of the cube, there is no enhancement. The actual enhancement provided by the cube is around 1700, which is quite impressive. So where we would like to take it eventually, we do have a very promising platform, silicon nitride, and I should mention that best quantum companies now like PsiQuantum, Xanadu, they actually using silicon nitride for a simple reason. The losses in this material are the smallest, smaller than in silicon, because two-photon absorption is small in this case. So it's a very, very promising, if not the most promising material for quantum photonic circuitry. So, and now we have the single photon emitters as opposed to this parametric down conversion way, which is a probabilistic way to make single photons. Here, potentially, we could make deterministic sources of single photons, and that's actually what we are working on. But to make these photons indistinguishable, which is required for many applications, so we would be able to create different cluster states, entangled states. So, and for that, we might need this plasmonic speed up, because the rate of emission most probably would not be not high enough. And for that, we plan to place all these plasmonic nano-antennas via these LPHYS'-based single photon emitters. And the same idea, of course, could be used also for other things like quantum frequency converters, for gates and for detectors. So we believe it's a very powerful and robust idea. In terms of what is next, so we want to optimize waveguides. It's actually known, and we just demonstrated it in our simulations or confirmed it in our simulations. If you take a very thin silicon nitride, which is sitting in silica, so then the losses could be extremely small, because basically all the energy is sitting in silica, and this a very thin, like 20 nanometer silicon nitride plate just simply gives you the direction where wave propagates. So that's really low loss waveguide. and we would like to combine it with these single photon sources. And that's the whole idea, actually. And the things which we plan to do next is to demonstrate this silicon nitride-based technology, for example, for quantum key distribution, polarization based, and that would be really big development, room temperature operation with such a pretty large count of generation of single photons. We hope to do this quantum key distribution, but this work is still in progress. Another thing to do is basically to demonstrate on chip indistinguishability of single photons. And for that, we plan to do this HUM interferometry right on the chip, and that's the next thing to do. That's what we plan to do next. Here, just to advertise, we, together with Jennifer Diane, we wrote this article about the way we see what's next for nanophotonics. It is in the latest issue of Physics Today, June issue. Here is the team which did all the work, and in the end, let me just put again the topics we discussed, and I would be happy to answer questions you might have. Thank you guys for your attention, and thanks again for putting this seminar together.
Okay, thanks a lot, Vlad. Do we have any questions?
Can I
Alexei?
go ahead and ask? I wonder, what are the prospects for generating photon pairs instead of single photons? Is there good use, or is it even realistic to think of photon pair production similar to parametric down conversion, but maybe in a cascaded 3-level system? What do you say about that?
That's a good question, but in case of silicon nitride, actually, this material has reasonably high Chi3. So therefore, to produce these entangled pairs of photons, the right process would be, instead of 3-wave mixing, to use 4-wave mixing, basically 2 pumps, and generate these entangled pairs of photons. And it should work, actually, because Chi3 is pretty high, and it gives additional advantages. So, and that's certainly what we plan to do. So, but the idea is to use Chi3. Alternatively, of course, you could bring some other material with Chi2, but that's exactly what we are trying to avoid. We want to have this all on silicon nitride, because when you hybridize your structure, it makes it more complicated and you lose some efficiency. So our goal is to employ Chi3, inherent Chi3 in silicon nitride, which is pretty good.
And still speed it up with the Purcell factor.
Right. I mean, if you're very lucky, as I pointed out, at least at low temperatures, we cannot say how strong is decoherence because, as I said, we instrumentation limited. But I mean, there is a chance that we would get indistinguishable photons without any plasmonic speed up. But that's it's probably the probability of this is very low, because typically spontaneous emission rate is around nanosecond, maybe 100 picosecond, but I don't believe it would be that short. So anyway, therefore, I expect, yes, we will need these plasmonic antennas to speed it up. And the simplest way, like to put it on top of this pillar, which create the single photons like a plasmonic cap or something like metallic cap, that's something we are starting to try to do. But yes, you're right. In the end of the day, we will need to bring these plasmonic antennas, none of them most probably on this silicon nitride platform. At least that's the idea currently.
Okay. Do we have more questions?
I have one question. So, thank you for your talk. Could you please inform magnitude of Chi3 nonlinear coupling coefficient for SPDC process?
I don't remember the just number, but what I do remember, when you compare it with other materials, it looks quite favorable. It's not like the best, but it's at the level of typical, let's say, Chi3 good materials.
Okay.
So, I mean, you could, it's a, I just don't remember the number, but if you look at the table, I mean, it's like, I believe it's even in the Voigt textbook, you could see, find this Chi3. And it's certainly at the level of really good Chi3 materials.
Mm-hmm. Okay, thank you.
Okay, do we have more questions? just have one quick one. So on the HBN, how close do you think you are to seeing single emitters in those magnetic?
You see that, I mean, well, I showed this specifically with boron vacancy. In this case, we, underneath of a cube, we have more than one emitter. Therefore, it's not single photon emitters. We do see enhancement, but it's not in single photon emitters. In our different experiment, which I didn't show here, we actually created these emitters with the FM tip. You just push it, HBN, you create a small defect, and actually it does act as a single photon emitters. The thing is that those single photon emitters which have been observed in HBN, they have relatively low efficiency. So the count is really, really low. You have to speed it up. An additional challenge in many cases of these emitters, the dipole moment is actually in the plane. When you do this plasmonic speed up, like putting HBN between metal film in a cube, of course, the enhancement is in the perpendicular direction. The high local field is perpendicular to the film, whereas the dipole moment of emitter is quite often actually in the plane. So we're still open for possibility to have really good single photon emitters. By good, I mean having really high efficiency, as opposed to what people observe. Or let's say with right orientation of dipole moment so that we could use plasmonic enhancement very efficiently. So it's promising, but so far we either see not a single photon, but with strong enhancement, like what we did with this boron vacancy, or we see single photon emitters, but the efficiency is not as high. So, but we keep working. It's not like it's fundamentally impossible. So we keep, now we're looking, for example, for carbon vacancy, which might be actually more promising. Let's see what happens. And
Okay.
we still would be happy to get really nice emitters based on nanodiamonds, as we discussed many times with you, Phil.
Yes,
so,
well, as you see, we're making more progress on that recently, so it's getting quite close now.
So basically, if the decoherence rate wouldn't be that crazy, like in the case of this nitrogen vacancy, closer to the rate of spontaneous emission, then you wouldn't need that much plasmonic speed up. And then we would be able to demonstrate this sources of indistinguishable photons.
Okay, so do we have any more questions? Okay, if not, we'll move on to our next talk by Donghee Sun.
Hello, can you all hear me?
Yes.
Okay, I'll share the screen. Okay, so first of all, let me thank the co-chairs of this seminar 10 for the kind invitation. And the title of the talk today is a coherent external emission from coupled cesium-lead bromide perovskite quantum dots in strongly quantum confined the regime. I'm from the chemistry department at Texas A&M, so some of the topics that I'm going to introduce may be less familiar to some of you. So let me go through slowly so that I can explain what I'm going to talk about well. So I'd like to acknowledge my students and also the funding agencies and the collaborator in the Texas A&M on this slide. Okay. The material system that I'm going to talk about today is a colloidal quantum dots made out of perovskite material, specifically cesium-lead halide semiconductors. The reason why I'm introducing this material is for the past 5 or not quite yet 10 years, but metal halide perovskite nanocrystal has been very popular as a new quantum dot, colloidal quantum dot materials as a photon source, either both coherent photons and incoherent photons. The reason why this material has been so popular is that, for example, color is extremely tunable. So I'm showing you a figure. So let me switch to laser pointer. So this is just a photograph of the simple photoluminescence from the colloidal solution of metal halide perovskite nanocrystals. You can change. You can have the visible and the UV and even the EIR emission simply by changing the stoichiometry of the materials and also changing the particle size if you want to take advantage of a quantum confinement of excitons. And also, compared to many other colloidal semiconductor materials, fluorescence quantum yield of this material has been very high. Sometimes it's nearly 100% of quantum yield. And also, these materials are very resistant to any structural defects that tends to decrease the quantum yield. However, there is one disadvantage of this material compared to many other known quantum dots, such as 26053 quantum dots. That is, this crystal is a very ionic. So this is composed of the cations and anions. So you can think of this as a very tiny salt. So if you put this material in a very polar liquid environment or moisturous environment, they are going to dissolve away. So that's one of the most serious cons of this material. However, if you put this material in the non-polar environment and if you avoid the moisture, this will be extremely good source of photons. And here I'm showing you some of the TM images. People can control the size of these nanocrystals from a few to over 10 nanometer. And from the tunability of the size and even the morphology, you can control the property of the light, not only the colors, but also the polarization, linear, the circular polarization, and so forth. Okay. One of the topics that I'm going to like to talk about today is coherent emission of photons as either superfluorescence or superradiance. To achieve that, people like to assemble these nanocrystals in the form of superlattices. Because of these quantum dots, the colloidal nanoparticles, one way to put them in superlattice form is simply just slowly drying it in solution phase. And what people have reported is that so this is a TM image of each individual cube-shaped nanocrystal, and if you dry them, you can have a micron scale. The superlattices are composed of millions of nanocrystals. And people have shown that superfluorescence is emerging from the superlattices. And you can see that the larger than 1 second order correlation coming from the superfluorescence of superlattices. And more recently, people have demonstrated that the superradiance can come from the electronically coupled array of quantum dots and so on and so forth. However, so far, most of the studies are trying to extract coherent photons out of these quantum dots were done using relatively using the quantum dots with a relatively small quantum confinement or no quantum confinement at all. So what I mean by the quantum confinement here is it's just a relative size of nanocrystals with respect to the exciton Bohr radius. So all these nanocrystals I'm showing here, which is about 10 or larger than 10 nanometer. So they are larger than the twice of exciton Bohr radius, which is 7 nanometer in this case. So therefore, if you want to take advantage of any confinement effect of exciton, you cannot do that with these nanocrystals. So a lot of people are trying to actually push that thing to the strongly quantum confinement region, because by imposing quantum confinement, you can achieve several things that you couldn't do in non-confined system. First of all, since you are enhancing the electron-hole exchange energy, you can sort of tune the exciton fine structure, specifically the energetics of the bright and dark exciton. Here, dark exciton, what I mean by that is that simply a dipole forbidden transition, which have extremely long lifetime and yet very bright, like a 3 or 4 magnitude longer lifetime than typical exciton lifetime, but still extremely very bright in terms of its light emitting capability. So my group spent some number of years developing the materials that can impose a strong quantum confinement in this particular material, and also try to understand the structure property correlation, specifically the properties of the exciton, both in energetics and its relaxation dynamics. And later on in this presentation, I will also show you some of our preliminary result, none of them published yet, that suggest that imposing a strong quantum confinement and using specific type of a surface ligand enhances superfluorescence. And also I will talk about the benefits of combining these colloidal nanoparticles with the resonance cavity to enhance both spontaneous external emission and coherent external emission. All right, so my talk will have 4 small pieces. I kind of already said that without showing this slide, but I will go one by one. So this slide shows TEM images of colloidal nanoparticles that my group synthesized several years ago. And so here you can see that, so by the way, so all these TEM images on the same length scale. So you can see that we can control the size from very tiny. So in this case, the size is about 3.5 nanometer. And that's a 6 unit cells of this particular crystal. So cesium, lead, halide. In this case, a halide is a bromine. So cesium, lead, bromide nanocrystals. And you can very finely tune the number of unit cells in the cube-shaped nanocrystals. So we can essentially control the size of the cube at the single unit cell level. And in this case, the size is much smaller than twice of external Bohr radius. So if you measure the external absorption and external emission peak, you can clearly see the signature of a quantum confinement. And also, the morphology of these are very uniform, and the size is also very uniform. And if you draw it slowly, even on the TM grid, you can get a spontaneous assembly of these nanocrystals to form the superlattices on the order of a micron size. And that this kind of superlattices will be used later to explore superfluorescence and superradiance in the later slide of this talk. And another nice thing about this material, synthesized chemically, is that you can not only get the cube-shaped quantum dots, but also you can get one-dimensional or two-dimensional structures, nanowires or nanoplatelets that they can encode another information here. For example, you can have very strongly linearly polarized light, and they can also assemble in certain ways. So this will be another way to potentially tune the property of light from the assembled structure of chemically synthesized colloidal quantum dots. And another thing that my group was interested in studying this material is that unlike in the other photon emitters that the previous speaker introduced, in these materials, if you change the size or morphology, it actually changes the exciton fine structures, and that it can alter the identity of the emitting state. So for example, in large the nanocrystals of the same material, the dipole allow the bright exciton that has nanosecond or sub-nanosecond lifetime is the major emitting species at every temperature that we could study from room temperature to below liquid helium temperature even. However, if you impose a strong quantum confinement, the relative energetics of a bright and dark exciton can switch. And at one point, you can have dark exciton that has a 10 microsecond lifetime to become the major emitting species. And that can be tuned by changing either shape or the size of these materials. And sometimes in the assembly of these nanocrystals, you can change the proximity of the nanocrystals, which affect the electronic coupling, which in turn changes the external fine structures that will that can potentially alter the nature of the emitting states. So my group was spending quite a bit of time understanding how the nature of the emitting states and also dynamics of the external recombination depends on structural parameters of these materials, including size, shape, and so on and so forth. Okay. I'm going to skip this one for now. Okay. So the first thing So once we mastered how to synthesize these materials, so with the control, the dimension, and the morphology, the one thing we wanted to learn is how to put them together in the self-assembled form with a controllable facet-to-facet distance and a controllable size. I didn't explain to you early on, but these nanocrystals, being colloidal nanocrystals, is a the organic molecules. So the reason why we need organic molecules decorating the surface is that, first of all, we need to maintain charge neutrality because these are the ionic nanocrystals. Depending on what ion is dominating the surface, you will have to compensate the charge with organic molecules with the opposite charge. The second reason why I need organic molecules is that molecules are formed sort of a protective layer so that these particles can suspend in the liquid without sticking together. So those are the reason why the organic ligands are typically needed for pretty much all colloidal quantum dots synthesized chemically. However, you can control the identity of the organic molecules on the surface. For example, the length of molecules or the binding functional group of the molecules. Then you can change the structure of the assemblies. So, for example, let's look at these two images. So this is a quantum dot. The TM image of the same quantum dot, but they look very different. The reason is they have different ligands. This one has very long ligands called the oleyl ammonium bromide, which has about the length of the 1.5 nanometer in total length. So the facet-to-facet distance is about 3 nanometer. So in this case, we replaced the lengthy the organic ligand, the very short inorganic one, so you can reduce the facet-to-facet distance in this is superlattice to a few angstrom. Okay, so here, so by changing the interfacial structure of a quantum dot, so we are able to control the facet-to-facet and also quantum dot to quantum dot distance, and we wanted to see how that affects the exciton fine structure and the dynamics of their recombination. So by the way, so in this particular study, the superlattice that we formed is only two-dimensional. So we used a relatively dilute solution of quantum dots, and we directly formed the superlattice on TEM grid. And the 2D superlattices formed the TEM grid that was directly characterized with the fluorescence of the spectrometer. And to make a long story short, so if you introduce the stronger electronic coupling between the quantum dots by putting them together and also reducing the facet-to-facet distance, one thing that was very prominent in this case is that you are changing the relative energetics of a bright and dark exciton. Specifically, you are changing the energy gap between bright and dark state, and introducing strong electronic coupling reduces the bright and dark state, and at the same time, it's accelerating the decay dynamics of both the bright and dark exciton. So this has some implication when you are trying to make a superlattices and also try to use either bright exciton transition or dark exciton transition as a photon emitting transition, and we need to really understand how the photon emitting property is correlated with the structure of an isolated particle and also structure of the assembled superlattices. Okay, so that was about the forming 2D superlattices and its impact, the impact of introducing electronic coupling on the exciton transitions. And here we are talking about the forming the 3D superlattices. Okay. And I'm showing you the TEM images here of the superlattice formed out of a 10 nanometer cesium lead bromide cube. You can see that on TEM grid itself, you can form several micron-sized superlattices. And if you zoom in, this is the image of individual superlattices, and each cube represented in this image is each particle. And if you look at the SEM image of the superlattices deposited on the silicon substrate, you can kind of see the cube-shaped superlattices on the order of a few microns. And now if you change the particle size, quite a number of things are changing. So of course, by the way, this is SEM images of a superlattices formed with a 4 nanometer quantum dots. And in this case, the size of the superlattices is slightly smaller. In some cases, instead of getting the cube-shaped superlattices, you get somewhat distorted structures. We occasionally see that that's because organic ligands sometimes tend to distort the lattice structure so that the symmetry of the superlattice can be affected by that. So the problem with this is that when you have smaller particles, the influence of ligand becomes stronger. So controlling the structure of a superlattice becomes a little bit more tricky. And if the organic ligand can influence the photon emitting properties of these superlattices, and that you will see more in the smaller nanocrystals than in the larger nanocrystals. Okay, I mentioned earlier that these nanocrystals have organic ligand on the surface to make it soluble and also give a structural stability and so on and so forth. So as a chemist, we have access to several different the kind of organic ligands that protects the surface. And the choice of the organic ligands depends on, well, a few of the guiding rules, but a lot of the cases we just have to try to put them and see how they behave. One of the things that we are looking for when we choose a ligand is that how stable the quantum dot is. So here, what I mean by stable is actual structural stability under more polar environment and also under light illumination. So here, I like to talk one specific type of organic ligand, which we call the zwitter ionic ligand. So zwitter ionic ligand has the functional group with the opposite charge, which functions as an anchoring group on the surface that tends to make these nanocrystals more stable. And because of that, when you shine the laser light to generate the super radiance or superfluorescence, they tend to survive longer. And then that is, of course, that are practical, the advantages compared to nanocrystals with ligands that make it less stable. Okay. So this is not our study, but one of the recent study that showed that when you use this particular type of the ligand, which we call zwitter ionic ligand, you can get the super radiance and superfluorescence a lot better than the nanocrystals are passivated with the other ligands. So in my group, we wanted to combine our ability to control the size of the quantum dots in the strongly quantum confined region with this chemical modification so that we can get a super radiance and the superfluorescence, which can also take advantage of easier interquantum dot coupling between the smaller nanoparticles. Okay, so these are some of our very recent work from last 1 or 2 months or so. So all of these are the unpublished, and some of the graphs are very crude because we didn't have enough time to make it look nicer. But anyway, so I want to show the comparison of these two, the photoluminescence made out photoluminescence coming from the superlattices of quantum dots passivated with a typical non-zwitter ionic ligand. In this case, it's olealamine bromide, which has one anchoring group, and the zwitter ionic ligand that has a 2 anchoring group that makes more stable and also more coherent. You can immediately see the differences in the the fluorescence, and it shows a little bit more signature of having superfluorescence, but the difference is not huge. But however, when we use fluorescence coming from the super lattices formed from the smaller nanocrystals, in this case we are using 4 nanometer, and we changed the ligands from olealamine bromide and zwitter ionic ligand, you see huge difference here. So here, the emission that's coming from the here, that's centered around the 480. These are the non-superfluorescence mostly, just emission coming from the non-coupled quantum dots. However, when you put the severe ionic ligand, you see two very different emissions. One, fluorescence coming from non-coupled quantum dots, more or less individual randomly emitting quantum dots, and superfluorescence with much narrower line width and a very huge at the Stark shift. And also, the lifetime at low temperature is a very short compared to typical lifetime at room temperature. At room temperature, the lifetime of the non-coupled fluorescence is 5 to 10 nanosecond, and this superfluorescence at low temperature has a lifetime of about 0.2 nanosecond. And when you isolate this fluorescence, and then when you measure second-order correlation, you can definitely see the larger than the background, the 1. So if you normalize this level to 1, so this is about the 30% higher. So this is definitely a clear signature of creating the superfluorescence coming from the smaller nanocrystals, where the superfluorescence is more facilitated by using the severe ionic ligand. Okay, and since we can we are forming these superlattices by simply drying it. You can have varying size of the superlattices. So here I'm comparing larger superlattice and the smaller superlattice. And interestingly, if you form a larger superlattice, you can have a superfluorescence at much higher temperature. So for the smaller one, we were able to observe a superlattice only below the 60 Kelvin. But for the larger one, we were able to observe a superfluorescence even up to 250 Kelvin. So we are hoping to see that maybe if you make a even larger one, we could perhaps observe a superfluorescence even at the room temperature, and this is an ongoing effort. And another thing that we thought that these self-assembled superlattices made out of a colloidal quantum dot is that it is compatible with a lot of other the structures that can enhance the emission. For example, in this case, we were trying to see whether we could take advantage of a microring cavity as a mechanism to enhance both spontaneous emission and also superfluorescence. And how much time do I have?
Including questions, 4 minutes.
Oh, okay, all right. What we wanted to do is they form a sort of a virtual the ring cavity made out of the quantum dots, and it's not easy to form the cavity of a quantum dot itself. But we recently found out that simply the spin coating the solution of a quantum dots on the pre-formed silicon nitride ring cavity, you can sort of have a the virtual cavity structure, even though the physical structure is not the ring. You can have a virtual cavity structure made out of the quantum dot film, and we were able to conclude that by looking at the doublet, the fluorescent structures in this resonance cavity, one you can assign to the fluorescence that is resonated within the silicon nitride ring, and the other secondary peak we were able to assign it primarily coming from which I call the virtual ring made out of the quantum dots. And we think that this the simplicity of the forming these rings intimately connected to silicon nitride, that we can take advantage of these microstructures to enhance the emission from the excitons. And the last thing that we tried is that seeing whether we can form the superlattices right on top of the ring. And this is a very the new result, which is only about a week old. When we use a severe ionic ligand, we think that we can form the superlattices on top of the ring, and that we can see the resonance emissions of a superfluorescence that can be enhanced by the resonance ring cavity. As opposed to this, even though you use the same quantum dot to form attempting to form the superlattices, if you don't use a severe ionic ligand and if you use the single anchored oleoammonium group, you see this the emission coming from only the isolated the individual nanoparticles. It is a 480 as opposed to 520 nanometer. So we think that the role of severe ionic ligand in forming more ordered superstructures and perhaps creating the more coherent superfluorescence is very interesting and still not very well understood. And we are trying to perfect the procedures to form the higher quality superlattices and also make it more compatible with the structures like a ring cavity to make it more practical source of coherent photons for future applications. And with that, this is a summary, which is just a duplicate of the outline, and I'll be happy to answer any of your questions.
Okay, do we have questions? Okay, I guess I have one. Do you have any feel for why this zwitterionic termination works so well?
It is not very well known. There are only a few published studies that suggested why. So one is since you have a two anchoring group, maybe it is freezing out the vibrational mode from the ligand that contributes to dephasing during the photon emission. And it also, I think, it helps to create a more ordered structure, the physically more ordered structure in the lattice. But still, a lot of it is not known yet.
Okay. So, any other questions?
Let me ask a quick question if there is no one else.
Yeah.
I wonder what you think about speed up. Emission speed up accompanied by spectral broadening, I guess, due to coupling into the cavity, per cell type of a speed up, versus super radiant speed up from a superlattice. What do you think about these two?
I think both are possible, and you can definitely put these superlattices in, for example, the plasmonic the structure to speed up. And I think that there has been some attempt, not with the superlattices, but a few clusters of nanocrystals is better. But sometimes one problem with these nanocrystals is that when these nanocrystals are too close to the, for example, plasmonic structure, you actually kill the emission. And that is a little bit of a problem using the Purcell effect, and specifically with the plasmonic structures.
Okay, thank you.
Okay, so if we don't have any more questions, let's move on to our next talk. The Zhenrong Zheng.
Can you see my screen?
Recording stopped.